Welcome to the Problems Channel Season 2, Episode 46, the episode which I titled Minuses to Move and Never Lose, because in this episode we will solve a problem that deals precisely with the distribution of the plus signs and minus signs over a 4x4 chessboard. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to get your bearings on this channel, to see what is going on and how does this channel work, and derive the most academic benefit for you from working with the material presented on this channel, is to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety. It's not that long, it's about 17 to 20 minutes long. Follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E46, we're given a complete 4x4 chessboard shown over here on the left-hand side of your screen with all 16 squares present. We're also given 15 plus signs and exactly one minus sign initially. And we're told that, for example, the minus sound, the single minus sound, is thrown at random onto this 4x4 chessboard. Let's say this minus sign lands in a square of that board. Let's say it lands over here, but it could be any other square. And once the placement of the sole minus sign is over, we take the remaining 15 plus signs and sprinkle them over the remaining 15 squares of this chessboard in the fashion one plus sign per square, so no square is empty, and precisely one and only one sign is placed into each and every square of this 4x4 chessboard. Then the rules of the game are quite straightforward. We're allowed to pick at any one time only one column of that 4x4 chessboard, not two columns, not three columns, not four columns, precisely one and only one column, or exclusively at this time. If we're not picking a column, we're allowed to pick only one row. Which one doesn't matter, we can pick any row, but again, it has to be one row, not two or three or four rows, and it is not allowed to combine rows with columns. The or in this case, usually in mathematics, or is understood to be inclusive. In this case, it has the exclusive flavor, which means that one move, let's say this move is executed on schedule every second, every minute, or every hour, pick your favorite unit of time, but every unit of time that move is executed, and that move means that we pick precisely one column at a time, or if it's not a column, it's a row. Which row doesn't matter, or which column doesn't matter. Once that decision is made, if we decide to work on a row, then all the plus signs in that row must be flipped to the minus signs, and all the minus signs in that row must be flipped back to the plus signs. Likewise, if we decide to act on one column, then we pick any column that we like. For example, the rightmost column shown over here. We roll through all four squares of that column and we flip all the signs in that column to their opposites. So these are the rules of the game, and the question is the following. If, let's say, we execute one move in this game every second, is it possible to put this 4x4 board into such a state that it is filled with nothing but 16 pluses? In other words, is it possible in a finite amount of time or in the finite amount of moves to basically, roughly speaking, erase the sole minus sign from the existence over here and fill the board with nothing but 16 plus signs, one plus per square? As we can see, the question or the very spirit of this problem is open-ended. So what does open-ended mean? A technical problem is open-ended if and only if the statement of that problem does not contain an exact outcome that may unfold in this technical problem. For example, in this case, we are not told to show that following these rules in a finite amount of steps or in the finite amount of moves or in a finite amount of time. It is possible to put the given 4x4 chessboard into a state where all 16 squares carry nothing but pluses, or we're not told that it is show that it is impossible. That outcome is not specified in the problem statement, and the burden of finding out which way the situation will go is precisely on us, the problem solvers. And this approach is perhaps in a stark contrast and in a stark difference from how most of the textbooks in most countries operate, because in most texts in most countries, what you will see in the problems and exercises is the exact outcome will be already given to you. For example, in a grown-up complex analysis case, for example, you will be told using the Cauchy's residue theorem that connects the residues of holomorphic functions with a certain integral, show that the following infinite sum of the squares of reciprocal whole positive numbers is equal to pi squared over 6. The exact outcome in this specific problem will be already given to you, and you will have to scratch the back of your head and figure out, how can I throw some integrals, compute some residues of holomorphic functions, and then some clever contour probably in the complex plane, and boom, show that this is the case. However, the way the all exact sciences, mathematics, theoretical physics, and computer science operate is exactly in the open-ended way, or in open-ended fashion, and not in a way when the precise outcome of this problem is already given to you. Why? Because the thin blue line of now in mathematics, theoretical physics, and computer science is very messy, precisely because that thin blue line of now is open-ended. When we're trying to discover or invent something new, we precisely do not know which way the situation will unfold. It can go this way or that way or this way or that way, and the burden of figuring out which way the situation will unfold is precisely on us. That is why, in order to prepare yourself for the bigger and better things to come, it is a good idea to use the material that we present on this channel as a dress rehearsal for the bigger and better things to come, because this is precisely how the situation will unfold, and this is precisely what you will be dealing with when you will be working on your, let's say, PhD in mathematics, theoretical physics, or computer science, and you will be facing precisely an open-ended situation. Now, precisely because of the placement of this problem in the sequence of problems on our channel, it is evident that this problem can be solved in a way that uses the invariant problem-solving approach. And the situation with this application of the invariant problem-solving approach to the process of finding or generating a solution to this problem is the following. If you know absolutely nothing about invariants and you have never heard about them in your entire life, then personally, I'm not really sure how can you solve this problem without the notion of an invariant. I think that you will have a very hard time doing so, but if you manage to solve this problem correctly on your own and without using the notion of invariant, I will be very curious to hear from you. Please do not be shy. Share your idea in the comment section. That's number one. Number two, you may be aware of the notion of an invariant implicitly or explicitly. Implicitly, for example, in middle school, this way, that way, maybe this precisely these words were not used, but fundamentally, in his elements in book 1, this is proposition 41, Euclid basically says that if you take any parallelogram, whatever it is, and then on the same base and on the same parallel, you construct a triangle, then the area of the triangle will be precisely 1/2 of the area of this parallelogram. And what conclusion can you draw from this? You see, the words invariant in this setting usually are not used for students, but now that we are, the smarter cucumbers, now that we're indoctrinated into all this invariant business, what can we say? Well, we can say precisely these words. The area of a triangle remains invariant under what? Under the condition that the length of the base and the length of the height of that triangle is one and the same. In other words, we can construct uncountably infinitely many triangles on the same base with the same height. They can go on and on and on like this, and all these triangles will have what? They will have one and the same area, which will mean what? Which will mean precisely that under the conditions specified, the area of these triangles remains invariant. Precisely, again, the specific words invariant under conditions or an invariant with respect to may not have been used, but implicitly this is there. So in theory, you are capable of drawing this conclusion. Very well. Explicitly, you may know about invariants also, for example, perhaps in upper middle school or in high school, or back in my time, that was, for example, I took the course on analytic geometry. That was year 1, semester 1. You were told about the formula that expresses the distance between 2 points. Between 2 points in the Euclidean plane, let's say, with the coordinates x1, y1, and x2, y2. And what is this formula? x1 minus x2 squared plus y1 minus y2 squared. This is the Euclidean metric. Remember, several episodes ago we discussed the so-called metric spaces. This will be precisely, this is one candidate, one popular candidate for a convenient metric. And what is this metric? Turns out this metric is precisely an invariant in the, let's say, Euclidean plane with respect to what? Well, if we translate the origin of the given coordinate system in any which legal way and put our new coordinate system over here, then in the new coordinate system, the numbers x1, y1, x2, y2 will become x prime 1, x prime 2, y prime 1, y prime 2. And once we do the corresponding manipulations, we will see that the structure of this here quantity will be one and the same. So on the parallel translation, this quantity remains what? Invariant. And in some sense, that means that the distance between 2 points on the parallel translation is preserved or remains invariant. And what else can we say? Well, under the rotation of the chosen coordinate system, again in the same plane, that distance will remain the same or invariant. This here expression will have the same structure and the same value, and also under reflection. So in this case, we go back to our favorite rigid motion. Exactly. So, but the challenge here is, even if you know and you were explicitly told about, you were explicitly given these words and invariant with respect to, the challenge here is the following. Fishing out from your web, fuzzy web of mathematical knowledge, where you have some nodes connected in some funny way. So fishing out the needed facts from your web of mathematical knowledge and connecting that with what is needed, in other words, connecting what you know with what is needed, is precisely the challenge. And that is one of the things that makes the process of solving technical problems so much fun. This is precisely connecting what you know with what is needed. Establishing this connection is precisely the situation where you need your ingenuity, creativity, and improvisational skills, because once that connection is made, usually, again, it's no guarantee, but usually from that point on, it's smooth sailing. But establishing that connection between what you know and what you need is quite challenging. And this is number 2. And number 3, let us say you are a regular customer on our channel, you are indoctrinated, you know what is going on. Once you read the problem statement, your nose already sufficiently well developed. I know what's going on. This is a problem on invariance, but here again, be careful. Precisely because of this phenomenon, the challenge of connecting what you know with what is needed. The bulk of the time, in real time, when and if you will be solving this problem on your own, will be buried or will be hidden where? Precisely in the search for a useful invariant that unlocks an elegant, beautiful, crisp, and perhaps a straightforward solution of that problem. So what this invariant could be? Well, we already described how the invariant problem solving approach works a couple episodes ago. If you missed that episode, then we suggest that you go back and watch that episode one more time. But if we want to apply the invariant problem solving approach to the process of generating a solution of this or that technical problem, we should try to decompose or sort the local material into 2 distinct piles. In one pile we put everything that does vary or does change, and into another pile that is usually much smaller we put all the things that do not change. Then we roll through all these things that do not change, and we try to see if one or several in combination of things that do not change, and we refer to these things as an invariant with respect to if a combination of these things can help us unlock a solution of this problem. One more time, I want to make sure, guys, that this idea is not lost on you. I want to make sure that I drive this idea home. Why do we like doing the open-ended problems on this channel? Well, again, using the example from the previous segment, it is one thing to be told, for example, use the Cauchy's residue theorem to show that the sum of reciprocal squares of consecutive whole positive numbers is equal to pi over pi squared over 6. It is one thing, because here you are told which tool to use, and you are told what exactly the result to drive towards to. Now, the real actually numbers, they're so complicated in the sense that most real numbers cannot be even named by us. In other words, most real numbers are so complex in their structure that we not only do not have, but we cannot even come up with a name for these numbers. Sometimes, on a rare occasion, certain situations, we can name certain real numbers, and here's an example shown over here. It turns out that the synonym for this here infinite sum is this specific real number called pi squared over 6. It is totally different thing to be given this problem over here. Look at this. What is the name of the real number that is hiding on the other side of this here infinite sum? We do not know. The first order of business with this kind of infinite sums, as you will learn, or you perhaps already know, is that we need to show if this infinite sum converges or not. And if it does converge, then what is the name of the real number that's hiding behind this here object? As I said before, the real numbers are so complex in their structure that most names cannot even be named by us fundamentally. Sometimes in certain situations we can come up with a name for a real number, and in this case we can. This actually open-ended problem was faced by a number of mathematicians more than 300 years ago. None of these mathematicians could actually answer this open-ended question, and for those who know a little bit about history of mathematics, who was the first guy who answered this open-ended question? Exactly, it was a Swiss-born mathematician, Leonhard Euler, who found a way to answer this open-ended question, and this is exactly why we're doing this type of problems. This type of problem on our channel will not be popular because this is not what this channel is. This is not who we are. This is not what we do. We like this type of problems. We like open-ended problems because this is much more difficult and this is much more fun. As such, this problem over here is open-ended. We now, because we are the indoctrinated cucumbers, we know that this problem can be solved using the invariant problem solving approach. We know that if we decide to apply this approach to the process of generating a solution to a technical problem, we should partition all the material in this problem into two distinct piles. In one pile, we put everything that does vary. Into the other, usually much smaller pile, we put things that do not vary. In this case, what does vary? Well, let's take a look at the local material. What do I have initially on the board? In our 4x4 square table, or some people will say it's matrix, over here I introduced the chessboard notation so I can have the more or less interesting title. Minus is to move and never lose. So in some sense, those of our viewers who pay attention already understand that the task over here in this, the answer to this open-ended question is no. It is not possible to use these legal moves and in any finite amount of time or moves or steps remove the minus from the board and make sure that all 16 squares are on the board. But what do we have right now? Right now we have 15, let's write it down, 15 plus signs and 1 minus sign. Wonderful. If we decide to apply this rule to this here state, again, you guys can in real time pick anything you like, but I will say, let's say we will act on the rightmost column over here. We have 4 pluses. Let me grab the red chalk, and according to the rule, all the plus signs are replaced with the minus sign. So we go minus, 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 and minus. Let us count now the number of pluses. What do we have? 4 and 3, 11 pluses. And how many minuses do we have? 4 and 1, 5. We have 5 minus signs. So from one step to another, every second, every minute, every bit, let's say we have a pendulum swinging, and on every swing we execute one move. So from one swing to another, from one step to another, what happens here? Well, what varies is the instantaneous number of pluses taken or from one configuration to another, and the instantaneous number of the minus signs. For example, in our initial state, we had 15 plus signs, and now we have 11. 15 is not 11, 11 is not 15. There is a change. Initially, we had 1 minus. After the first move, we have 5 minuses. 1 is not 5, 5 is not 1. This is the change. Very nice. What else changes over here? Well, if we pay close attention, then we can introduce the following notion of an immediate neighbor. If you write all sorts of games, for example, in some time I used to write lots of this type of games using the Java and the Swing programming library. You can find some of these samples on the on my GitHub repo. But the immediate neighbor, for example, let's concentrate on this square over here. Who are the immediate neighbors of this square? Well, we will mark this one, this one, this one, this one, and this one. These are the immediate neighbors. So in this problem, in addition to the instantaneous number of plus signs and minus signs on the board from one legal move to another that changes, what can change? What may change is the content of the immediate neighbors. For example, for this square, the immediate neighbor, remember, in the initial configuration was the plus sign, but now it's a must sign. So this is plus is not minus, minus is not plus, so there is a change. The content of this immediate neighbor, this guy over here, used to be what? In the original configuration, it used to be a plus, now it's a minus. There is a change. So in addition to the instantaneous number of the plus signs and the minus signs on the board from one transition to another, what else can change is the content of the immediate neighbors of a given square. For example, the contents of the immediate neighbor of this square also change, and the contents of the immediate neighbors of this square over here change here, 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 and here, for example. And we can also kick maybe some more ideas around. You guys, if you find something else that can change and something that can vary in this problem from one legal move to another, don't be shy, write your ideas in the comment section. But in the next segment, we will start looking at material, at a useful material that does not change. As I mentioned before, even under the best of circumstances where you're not only aware of the notion of an invariant, but you know all too well that this specific problem may be solved using an invariant with respect to, when you know everything, the odds are still stacked against you in some sense, because the bulk of the time in real time when you will be solving this type of problems will be buried or hidden in the open-ended search for a useful invariant. So how does the notion of invariant may help? Well, if we find a quantity that is invariant under, let's say in this case, any legal move, then we can try to, for example, compute the value of this invariant in the initial state when we're given only 1 minus sign and 15 plus signs. And then, because precisely we claim that the value of this quantity will remain one and the same after each and every legal move, we can compare the value of that quantity or the value of that invariant with the configuration that is requested from us when the board is filled with nothing but 16 pluses. And this is where the idea that I tried to tell you guys before comes to the surface, that not all invariants are created equal. An invariant is useful for us in this specific case if and only if it can detect the difference when it is applied to all the items of interest can detect the difference between all these items. In other words, in our case, we want to be able to take this invariant quantity, and we want that quantity to be able to have enough tactical juice in it to distinguish or discriminate between the initial value that corresponds to the initial configuration and the destination or target or requested configuration. So what can be an invariant over here? Maybe if any one of you guys comes up with a different invariant, then again, I would be very happy to hear from you. I would be curious to see if there are any other invariants in this problem, but here is one idea. Again, how do you come to this idea in real time? It's honestly a complete mystery to me. I've been trying to track this process down and do all sorts of problem solving experiments and see how these things come about. They can never catch it. But in your travels, in your way, you can act in one way. Here, for example, and maybe it so happened that I was converting one of my chapters on the book of group theory for all, an elementary introduction to the theory of groups. I was writing this chapter about sample multiplication tables, and it so happens that the two numbers +1 and -1 form precisely a finite this will be what, +1, this will be -1. It will be finite commutative, and in this case cyclic group of order 2, where the product of these guys here will be +1, -1, here will be -1, and here it will be +1. The identity of this group is the number +1, and these two numbers also, if you are aware of the finite and commutative multiplicative group of roots of unity, it will be precisely +-1 ± I. So again, it depends. You don't have to know any of this. It's all your mileage will vary. So how you arrive at these ideas depends on your level of maturity, knowledge, and experience. But here is one idea how to come up with an invariant. Let us replace all the plus signs. All the plus signs will be, let me use the blue chalk, will be taken or replaced with the +1. So far so good. And conversely, the +1 will be taken in, the +1 will be taken just into a plus. And every minus we use what? We use the red chalk, and every minus will be taken into a minus to the negative unity, -1, and conversely. And what does this maneuver over here represent? Come on, guys, think about it. What does this maneuver represent? What do you guys think? Okay, who said that? Correct. This is the application of our problem-solving approach that was the first one that we studied, that we began that study in season 1. This is called what? Transform and conquer. Exactly. We executed what will now happen to be a successful transformation. All the pluses became +1, all the minuses became -1. And then what do we do? What is the invariant? What is the potential invariant in this problem? Well, an invariant in this problem could be the following: the product of all the +1s and -1s on the board at any one time. This is our thinking, this is our idea. First, we remember that here, let's say this could be many things, it could be complex numbers, but let's say pretend that these are integers. Integers commute under multiplication, which means that for any two integers km, it is the case that k times m is equal to m times k. So far so good, which means that once we replace all the pluses with +1s and all the minuses with -1, we can multiply these numbers in our 4x4 chessboard in any which way. Row by row, column by column, actually diagonal by diagonal, any which way, doesn't really matter. The value of the product will be one and the same. So initially, let us say, let me erase this once you guys understand what's going on, using the fact that the integers commute under multiplication. Let's say the value of the product, we'll designate it with P, of 16 numbers, P16, at the initial unit of time, at the initial time t equals 0. So initially, at the point 0 will be what? Evidently, this will be, what is the value of this product? It will be +1 raised to the 15th power times -1 raised to the first power. What is that number? Of course, this is -1. So how can we show that the value of that product will remain invariant under any legal move? Well, one way to do so is to examine all the possible legal moves, and we will do that in the next segment. On the surface, it may seem that we have 5 distinct legal moves or 5 distinct cases of distributions of plus signs and minus signs in 4 squares of our chessboard that make up one column or one row. And what are these possible combinations of things? Well, first we can have 4 plus signs and 0 minus signs. This was the typical case in many columns initially, and rows as well, when we had only 1 minus in the row or in the column and 3 plus signs. And then what we have to do now is do the one of the favorite Eulerian tasks of finding in how many ways number 4 can be represented as a sum of 2 positive integers. We can also have the case when we have what? When we have 3 plus signs and when we have 1 minus sign, that's the second case. We can have 2 plus signs and 2 minus signs. We can have 1 plus sign and 3 minus signs. And what else can we have? We can have 0 plus signs and 4 minus signs. But are all these moves really that independent with respect to our rules? Or some of these rules can be made or shown to be equivalent. Recall that earlier we told you that the moment we are done with studying this or that dedicated problem-solving approach, then it doesn't mean that we should forget about it. On the quite the opposite, we should incorporate that newly studied problem-solving approach into our daily problem-solving experience. So far, we saw how the transform and conquer problem-solving approach can be used in addition to the invariant over here when we transformed each and every plus and minus into +1 and -1 correspondingly. And now we will use another problem-solving approach that we studied. And the name of that problem-solving approach is reverse order. Remember that when we studied that problem-solving approach, we gave you a parabolic analogy, if you will, or some sort of believable analogy when we can use a camera to record the process that unfolds. Then we can stop the camera and then we can play that recorded movie in reverse flow of time or in reverse order, and retracting the steps in that reverse order sometimes allows us to help solve a technical problem. Here, however, we need to be careful because there are limitations to this vague analogy with recording a movie and playing it in reverse order. Why? Because anyone can do that in their home. It's completely safe. Actually, go ahead and do this at home and take a piece of paper, and you can see that applying very little effort, the piece of paper can be torn apart, but using the same small amount of energy or force that we generated when we rip this piece of paper apart, we cannot put it back together. Now, if we take a movie of us ripping this sheet of paper apart and we play it back, yes, on movie it will look like we're putting it back together. However, this is where the limitation comes in, where this is where this analogy breaks. In reality, we cannot put this sheet of paper that we tore apart together in the real situation, and this is an example of a process that is not reversible. Later in physics you will learn that it has to do with the so-called adiabatic processes, but in our case certain things are reversible, because remember, due to the mechanics of the rule, every plus becomes a minus and every minus becomes a plus. These two guys in a way crisscross when they transform. One transforms into another and another transforms into one. Out of 5 seemingly distinct possible permutations of pluses and minuses in any 4 squares that make up a row or a column of our 4x4 chessboard, which ones are really equivalent? Let's think about it. Well, when 4 pluses become 4 minuses, if we replace, like, or remember we did it in the rightmost columns, when the 4 pluses are flipped into 4 minuses, we record that movie, we play it back. Not only we will see 4 minuses becoming 4 pluses, but in reality this is a totally reversible process. So when 4 pluses become 4 minuses and 0 minuses stay where they are and 0 pluses stay where they were, then this pair of legal moves becomes what? Becomes equivalent. When we examine the multiplicative outcome of this transformation, it will be the same as the multiplicative outcome of this transformation. What else? Well, when 3 pluses become 3 minuses over here and 1 minus becomes 1 plus over here, these two moves also multiplicatively seem to be equivalent. This is what we think right now. In other words, if and when we examine the multiplicative consequence of this transformation, when 3 pluses become 3 minuses and 1 minus becomes 1 plus, we think that that transformation will be exactly the same when 1 minus becomes 1 plus becomes 1 minus and 3 minuses become 3 pluses. So these two guys are equivalent, we also think. And now we only, instead of 5, we only have to do what? Now we have to only examine 3 distinct cases. For the first case, let us assume that at the moment of time t equal to k, our product of 16 plus 1s and minus 1s, which we'll designate with p16 at the moment of time t equals k. Let's say this time flows every second. We make a decision. Is some value. We do not know what it is, but we'll just assume that's some value. And we make a decision to pick a column or a row that has nothing but 4 plus signs in it. That will correspond to our first and fifth case that we just showed you in the previous segment. 1, 2, 3, 4. 4 plus signs. What does that mean? It means that once that decision is made and we want to concentrate on this here column, we can represent our product of 16 plus 1s and negative 1s as follows. The product of 4 pluses plus 1s in the chosen column or row plus the product of the remaining 12 plus 1s and minus 1s in the board, which whatever it is, we do not know, but we also do not care because this is how the multiplication of integers works. The product of 4 plus 1s and the product of the remaining plus 1s and minus 1s, whatever it is. Now, in this case, what is the value, multiplicative value of the all the plus 1s that are in this column? Well, this will be plus 1 raised to the fourth power. And what is the result of this multiplication? Plus 1 times plus 1 times plus 1 times plus 1. It is plus 1. Now, according to our legal rule, all pluses become minuses, as we saw over here. So now, instead of plus 1, we have negative 1, negative 1, negative 1, negative 1. And what is the value of the product of 4 negative 1s? Well, it will be negative 1 raised to the fourth power. Negative 1 times negative 1 times negative 1 times negative 1. And what is that value? It is a plus 1 again. You see here, we record this legal move this way. This is the symbolic representation of this transition from 4 pluses into 4 minuses. But recall our previous comment about using the reverse order problem solving approach. We can pretty much take 4 negative 1s, multiply them through, obtain 1 first, before the transformation began, before the move, and then obtain what? 4 plus 1s, which also when multiplied produce 1 plus 1. This is what we mean when we say that we apply the reverse order problem solving approach in this case. And the case is when 4 pluses become 4 minuses or 4 minuses become 4 pluses are multiplicatively equivalent. This is captured over here. Wonderful. And what does that mean? That means that we'll continue writing equals. That means that the value of the product of 4 integers in that column will be the same at the moment of time. Remember that this transition from 4 pluses to 4 minuses or 4 minuses into 4 pluses happens when k changes to k plus 1 after the next move. K plus 1, just like so. And because we did not touch any numbers in the remaining 12 squares of the board, that number over here survives that move without any change. It is what it is. So P12 at K plus 1. That much should be understood. And what does that mean? Well, this product of 4 integers and 12 integers is precisely the value of the product of our 16 integers at the moment K plus 1. And we just proved that under the legal move, when 4 pluses are changed into 4 minuses or 4 minuses changed into 4 pluses, the value of our proposed quantity, called the product of all 16 plus 1s and minus 1s on our 4x4 board, remains what? Remains unchanged or invariant. Now we will take on the case of 3 pluses and 1 minus, or 3 minuses and 1 plus. Let us assume that at the moment of time t equals k, we decided to act on a row or a column of our 4x4 chessboard that contains precisely 3 plus signs and exactly 1 minus sign, as shown in the bottom row on the left hand side of your screen. This could be a row that contains that many plus signs and minus signs, or there could be a column. What is the multiplicative value of that formation before the move is made? Before the move is made, the multiplicative value of this formation is given by 3 copies of 1 raised 3 copies of 1 times 1 copy of -1. Evidently, this will be -1. Do you agree? Plus 1 times plus 1 times plus 1 times -1, it's -1. And after the move, what happens over here? After the move, the 3 pluses become 3 minuses, and 1 minus becomes 1 plus. So the multiplicative value of that formation after the move is given by what? It is given by 3 copies of -1 minus 1 raised to the third power, and the product of 1 copy of +1. What is the value of that product? Is -1. So that is an equal sign over here. And this is another demonstration of the idea that why we say that multiplicatively certain rules are equivalent. That means that if we find a row or column that has precisely 3 minus signs in it, let's say over here we change in this column, we change all the pluses to the minuses. So we have, let's say, what is it? Minus, 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 minus. In this case, we have a row that has precisely 3 minus signs and 1 plus sign. And that means that before this particular column is acted on by our legal move, what is the multiplicative value of that, let's say, that formation, that row? 3 copies of -1, 3 copies of -1, and 1 copy of +1. And after the move is carried out, what happens? The 3 negative ones become 3 positive ones, 3 copies of +1, and the sole +1 becomes the sole -1 times -1, and the value of that product is 1 and the same. And again, before we carried out this move at the time t equals k, the value of the product of all the numbers on the board was p16k. It can be represented as a product of 2 entities, the product of 4 numbers in the chosen formation, in the chosen row or column, times the product of the numbers in the remaining 12 squares. We don't care what it is. The product of 4 numbers survives the transition from k to k plus 1, which means that it survives the transition according to the rule described over here. And the remaining product of the remaining 12 numbers remains unchanged because we did not touch these numbers. Again, we prove that the value of the product of all the numbers on the board at the time k and at the time k plus 1 remains what? Remains invariant. Lastly, let us assume that at the moment of time t equal k, we decided to act on a row or a column that has precisely 2 plus signs and 2 minus signs in it. And then before that move is made, actually, again, once that decision has been made, then whatever the product of all 16 plus 1s and -1s on the 4x4 board is, we designate it with p16 times k. It can be partitioned into a product of 2 pieces. One piece is the product of all 4 numbers in the chosen formation times the product of all the plus 1s and -1s in the remaining 12 squares, whatever they are. Before that move is carried out, what is the multiplicative value of such a row or column? Well, evidently, it is given by what? 2 copies of +1, 2 multiplicative copies of +1, and 2 multiplicative copies of -1. +1 times +1, -1 times -1. And after that move is made, so we put the equal sign over here optimistically. After that move is made, what? 2 pluses became two minuses became two pluses, and two pluses became two minuses. So in that case, the multiplicative value of the formation is still given by negative 1 raised to the second power times positive 1 raised to the second power as well. Plus ones became minus ones became plus ones. Again, the value of this formation again is one and the same. What is it? Exactly, this value is 1. It is plus 1. So that means that the value of the chosen four numbers at the time k survive the transition to the next move at time k plus 1. The value of the 12 numbers that we did not touch evidently produce the same product, manufacture the same product. So the value of the product of all the numbers on the board before that legal move and after that legal move is again one and the same. And what have we shown? We have shown that under any legal move, the quantity to which we refer as the product of all the plus ones and minus ones on the 4x4 chessboard remains invariant. Consequently, what we have proved is the following. The value of all the numbers on the 4x4 board when multiplied is negative 1 at the beginning, and it remains one and the same after any number, after any finite number of such moves. So we'll record it as the product of 16 numbers on the board at any time k for all k equal to 1, 2, 3, and so on. This is precisely what it means when we say that the product of all the numbers on the board is invariant under any legal rule. And again, remember the mechanics of the transform and conquer problem solving approach. We solve the problem in the transformed setting, then we do the reverse transformation, and that reverse transformation is very straightforward. The plus 1 corresponds to a plus, the negative 1 corresponds to a minus, and now we go back to the original problem statement and we inquire, is it possible to use nothing but a finite number of legal moves and put the board into a state in which it is filled with nothing but 16 pluses? Well, in that case, the product, let's write it down, the product of all 16 pluses on the board after some mysterious number of transformations supposed to be what? Supposed to be plus 1, because if we multiply 16 plus 1s, plus 1 raised to 16th power is still plus 1. So the product of all the numbers on the board in the requested or required configuration must be plus 1, but plus 1 is not equal to negative 1, not equal, and negative 1 is not equal to plus 1. So when we transform all this from the language of mathematics into plain English, that means that the answer to this question is the following. No, it is not possible to put the board from the initial state that we agreed upon into a state where it is filled with nothing but 16 pluses in any finite number of legal moves as described in the problem statement. And here again, for those who are new to the whole idea of solving problems, I recommend that you guys put this video on pause and walk away and think about it on your own, that we managed to generate this proof using the idea of an invariant, but we potentially circumvented a humongous amount of work, because if you decide to prove this statement that it is now that the cat is out of the bag, and we prove that it is impossible to do what is requested in this problem, which way without using the notion of an invariant? Well, in theory, you can try to combinatorially somehow come up with all the possible permutations of transformations of the numbers shown on board, and I'm not even sure if that can be done. You would have to, by the looks of it, put the minus sign initially into, let's say, one corner that takes care of all the corners. Then in this here square, it will take care of the squares like this, and to take care of this one of the smaller squares, probably or one over here, and start examining all possible ways in which the pluses can be taken into minuses, minus into ones, and then it's not even clear, even if you can, if it's possible to enumerate combinatorially somehow all the possible ways in which the board can be manipulated officially, and then on top of that show that no matter which manipulation you do, you can never obtain all 16 pluses on the board. This is the volume of work that is cut out for you if you do not want to use the idea of an invariant. Now, this is it for the mathematical problem S2E46, and we will move on to a new challenge next. Our next challenge will be a problem in mathematics, and it will be numbered S2M49 as shown over here, and the setup in this problem is the following. We're given 3 grasshoppers shown here in blue: grasshopper 1, grasshopper 2, grasshopper 3. All of these 3 grasshoppers sit in different vertices of a unit square. Unit square, 1 by 1, the distance between the sides, or between the immediate neighbors, immediate vertices of the square is 1, and every second, let's say, one, any which one grasshopper, which one doesn't matter, a random grasshopper jumps over another randomly chosen grasshopper by the distance that separated the two initially. In other words, from this initial configuration, let us say we have the 3 grasshoppers sitting in the vertices of a unit square as shown over here in the lower left, lower right, and the top right vertices. For example, you can experiment with other initial arrangements. The possible legal jumps over here are the following. The bottom left grasshopper can jump over the bottom right by the distance of 1 over here, like so. And consequently, the bottom right grasshopper can jump over the bottom left grasshopper, the distance that separates them 1 over here, like so, to this destination. Let me show it maybe highlighted in red, over here and over here. Now, in the same exact fashion, the top right grasshopper can jump over the bottom right, like so, and fly 1 distance past this grasshopper, because the initial distance between them is 1. So this guy can jump over here, and conversely, this grasshopper can jump over this one by the distance that separates them initially, 1, into this position over here. Likewise, diagonal jumps are also perfectly valid. For example, the upper right grasshopper can jump over lower left grasshopper by the distance what? Square root of 2, and fly the distance that separated the two initially past the grasshopper over which the jump is executed. So he can jump over here all the way. Likewise, this grasshopper who sits in the lower left vertex of the unit square can jump over the grasshopper that sits in the upper right vertex of the unit square by the distance that separates them initially, square root of 2, and fly over here into this point, and this distance must be equal to this distance. Let's mark it this way. This distance must be equal to this distance here and here, and likewise this distance must be this one, and this distance must be this one. These are the rules of the game. And let's say every second, as I explained, any random grasshopper jumps over any other random grasshopper, and the question in the problem is the following. Can it so happen that in a finite number of legal jumps that I explained, that unfold over here, can these 3 grasshoppers find themselves in the vertices of a 2 by 2 square? So initially they sit at the vertices of the unit square, 1 by 1 unit square. Executing a finite number of legal jumps, can they find themselves at any point of time, or after a finite amount of units of time goes by, in the vertices of a 2 by 2 square? Think about it. Again, the type of this problem is open-ended, as I explained at the beginning of this episode. If you think that it is possible, then you have to show a legal combination that starts from this position or from any position, and then puts the 3 grasshoppers into the vertices of a 2 by 2 square. If you think it is impossible, then you have to generate a convincing proof that no matter what happens, no matter how grasshoppers jump around, in this case, they can never find themselves in the vertices of a 2 by 2 square. Good luck. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2M49.